All right, so now we're going to take a look at the ratio test. In example 2, we found the radius of convergence of a geometric power series by using the fact that the absolute value of r, which is your common ratio, must be less than 1 for a geometric series to converge. If a series is not geometric and we cannot easily relate it to one by differentiation or integration, kind of like what we did on the Taylor polynomials, then we're out of luck. We need a new tool, and the best one in the shop is the ratio test. All right, so for the ratio test, it says let this be a series in which a sub n is greater than 0. So this is going to be what is called a positive term series. For all n, what we're going to do is we're going to form this ratio, a sub n plus 1 over a sub n, which means you can take any term in your series and divide it by the previous term. Now, in a geometric series, this is your common ratio. On the ratio test, this does not apply only to geometric series. This can apply to a lot of different series. And what we're trying to do is not determine if it is a geometric series. We're trying to determine if it behaves like a geometric series. And I'll explain that a little bit further in slides to come. All right, so here are the 3 conditions that we are going to be looking at. If the limit of as n approaches infinity of a sub n plus 1 over a sub n, so the limit as n approaches infinity of this ratio, if it comes out to be greater than 1, then your series is going to diverge. So even if this comes out to infinity, that's greater than 1, which means it would diverge. If the limit as n approaches infinity of this ratio is less than 1, that means that your series will converge. And if the limit as n approaches infinity of this ratio is equal to 1, then the ratio test is inconclusive and we would need to use some other test to determine convergence or divergence. So the idea behind the ratio test, like I said, is to see if long-term the given series behaves like a geometric series. For a geometric series, this ratio is a constant, the common ratio of the series, and only if this is less than 1 do the terms shrink fast enough for the series to converge. In the ratio test, we no longer suppose that the ratio of successive terms is constant, but we are saying that if that ratio eventually gets and stays below 1, then the terms will decrease at a rate on par with a convergent geometric series. Recall that the terms of a convergent geometric series go to 0 really fast. If we can show via the ratio test that a given series has terms going to 0 this quickly, then that will establish the convergence of the series. All right, so let's take a look at an example here. If we take a look at these terms, 8 plus a fourth plus 2 plus 1 plus a half plus a fourth plus an eighth plus a 16th, and so on. The terms of this, you are getting the next term in the series by multiplying by a half. What that means is that this is a geometric series because we're multiplying by the same value each time to get the next term in that series. And so if you were to write this using sigma notation, this would be 8 times 1/2 raised to the n, where we are going from 0 to infinity. All right, so that means when n is 0, this is 1/2 to the 0 power, which is 1 times 8, gives you 8. When n is 1, you get 8 times 1/2 to the first power, which is 4, and so on. This series will converge. This is a geometric series, and anytime you have a geometric series where your common ratio is less than 1, that series will converge to some value. All right, so let's think about this series over here from n equals 0 to infinity, and we'll just make this a fairly easy one here. 1 over n factorial. So we're going to establish that ratio of a sub n plus 1 over a sub n. Well, a sub n plus 1 is going to be, what that means is putting n plus 1 where the n is. All right, so you're going to get 1 over n plus 1 factorial times, and then the reciprocal, because it's dividing by a sub n, which means we're going to divide by the original fraction, which means we're going to multiply by its reciprocal. And the ratio test says that the limit as n approaches infinity of the absolute value of this. That's what we need to look at. Well, now, n factorial over n plus 1 factorial if you think about n factorial over n plus 1 factorial, n plus 1 factorial means n plus 1 times the next smallest number, which is n, times its next number, times its next smallest number, times its next smallest number, and so on, which means times n factorial. So those two cancel out, leaving you with 1 over n plus 1. Now, this is equal to 0. The limit as n approaches infinity of this is equal to 0. That is less than 1, which means this will converge. Now, let's think about writing out the terms of this series. So the first number, or first term in this series would be when n is 0. So that would be 1 over 0 factorial, which is 1, plus, and then when n is 1, you get 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial, which is 6, plus 1 over 4 factorial, which is 24, plus 1 over 5 factorial, which is 120, and this goes on forever there. Now let's look at the terms of these two series. See, in this series, we multiplied by 1/2 each time, and these fractions were declining enough or getting small fast enough to say that this converges. Now, these are also getting multiplied by a fraction each time. But that is not, that fraction that we're multiplying by each time is not the same number. So over here you had a common ratio, here you do not have a common ratio. But this is going towards 0 fast enough to say that it is going to behave like a geometric series. And therefore this series will converge. And this is the ratio test application there. All right, so let's take a look at some of these examples here. Now, the first one, we just did that one, so I'm going to skip over that one. The next one, if we apply the ratio test, this will be the limit as n approaches infinity. Absolute value, 3 raised to the n plus 1 over n plus 1. And then it's, again, remember, it's a sub n plus 1 over a sub n. And so we're going to divide by a sub n, which means multiply by its reciprocal. So times n over 3 raised to the n. All right, so we're going to simplify this a little bit. Now, 3 raised to the n plus 1 over 3 to the n. Let's think about these two terms right here for a minute. For reducing this, this would be equivalent to saying, oh, let's say that you had 3 to the 10th over 3 to the 9th. 3 to the 10th over 3 to the 9th is just 3. Or if you had 3 raised to the 8th power over 3 raised to the 7th power, that's equal to 3. Or 3 to the 5th over 3 to the 4th. It's going to reduce to 3 no matter what. So therefore, when you see something like this, 3 raised to the n plus 1 over 3 to the n, that's going to reduce. Now, algebraically, you can also think of this as 3 raised to the n times 3 to the first over 3 to the n, and those cancel out, leaving you with 3. All right, so in any case, this comes out to 3 times, and then we still have the n over the n plus 1. Now, the limit as n approaches infinity of this is going to, this is a spit in the ocean situation, so the limit as n approaches infinity of this is equal to 1, because n over n is 1. What that leaves us with then is going to be 3 times 1, which is 3. This is greater than 1, which means this series diverges because that value is larger than 1. All right, so look at the next one. Again, start out limit as n approaches infinity, absolute value 1 over square root 2n plus 2, because we put n plus 1 in place of n, times the reciprocal, and so that's going to give us the limit as n approaches infinity of square root of 2n over square root of 2n plus 2. Now, this also is spit in the ocean like we did in the previous problem, and so limit as n approaches infinity of the leading term over the largest value here is going to give us 1, and so this limit is equal to 1, which means this is inconclusive. All right, so example 3 shows some of the strengths and weaknesses of the ratio test. It works very well on series whose terms involve factorials and exponential factors. And when I say exponential factors, I mean something raised to the n power, because of the way these types of things cancel when put into the fraction a sub n plus 1 over a sub n. So when you see a factorial, you should almost always think ratio test. For power terms, like in the third series, this one right up here, which is essentially like n raised to the negative half, the ratio test is typically inconclusive. All right, so let's use the ratio test to determine whether the following series converge. All right, so this is going to start out like always, limit as n approaches infinity, absolute value, put n plus 1 in place of n. That makes this n plus 2 squared, times the reciprocal, so n plus 1 squared over n. Now this becomes limit as n approaches infinity. So we cannot really reduce anything here. So let's think about what's happening in the numerator. You have n plus 1 times n plus 1 squared, which actually becomes n plus 1 cubed. In your denominator, you have n times n plus 2 squared. And if we think about the spit in the ocean situation here, the leading term in the numerator is going to be n cubed, and the leading term in the denominator is going to be n times n squared, which also is n cubed. So you get n cubed over n cubed, which is 1. And therefore, the ratio test is inconclusive on this particular problem. All right, so the next problem, we could try ratio tests here. Would not be the most efficient way, but we can see what happens here. You're going to have 2n plus 2 factorial over 2n factorial, which is limit as n approaches infinity. We can reduce this to 2n plus 2 times 2n plus 1 times 2n factorial over 2n factorial, which these will cancel out, leaving us with limit as n approaches infinity. This would be 4n squared plus 6n plus 2, which is infinity, and that is larger than 1. Therefore, this diverges. All right, now, easier way of looking at this is to think about the nth term test, because in order for a series to converge, your function or your series must, the limit as n approaches infinity has to go to 0. And if you think about 2n factorial, as n gets bigger, these values are just going to get bigger and bigger and bigger. So there is no possible way that this is converging, because this does not even pass the nth term test. The nth term test says that in order for a series to converge, the limit as n approaches infinity has to approach 0. Well, this does not approach 0. This goes to infinity. Therefore, it cannot converge. Now, be careful with the nth term test. Just because a series goes to 0 does not mean that it necessarily converges. For example, part A. The limit of this right here, the limit as this approaches infinity, that goes to 0. However, this does not necessarily converge. It's inconclusive. All right, and the last problem we're going to do right here on this part is the limit as n approaches infinity of 2 raised to the n plus 1 over n plus 1 factorial times n factorial over 2 raised to the n power. All All right, so if we reduce this a little bit, 2 to the n plus 1 is going to reduce to just a 2 times, and then, actually I don't need to put times there, the n factorial over the n plus 1 factorial will reduce to n plus 1, and the limit as n approaches infinity, this is equal to 0, which is less than 1, therefore this will converge. All right, so let's consider this power series right here. For this series, a sub n is equal to this, but this means that a sub n is not necessarily positive. It's bad because of one of the hypotheses of the ratio test is that a sub n is greater than 0 for all n. It turns out that this is good enough. In fact, in some ways it's even better to look at the absolute values of the terms of the series. Instead of applying the test to a sub n equals this, we're going to apply it to the absolute value, which we have already been doing because I wanted to get you into the habit of doing absolute value, even though all the terms we were looking at before were positive values. All right, so let's take a look at some examples. This says determine the radius of convergence for the power series. So the first thing we need to do is apply the ratio test and determine if this converges or not. All right, so we're going to say the limit as n approaches infinity of the absolute value of x minus 3 raised to the n plus 1 over 2 n plus 2, because we put n plus 1 in place of n, times 2n over x minus 3 raised to the n. All right, we can reduce a couple of things here. So now, like before, x minus 3 raised to the n plus 1 over x minus 3 raised to the n. Well, if you have x minus 3 to some power, and this one is 1 power less than that, that will reduce to just x minus 3. And then we have times 2n over 2n plus 2. Now, if we think of this as the limit as n approaches infinity, this is going to go to 1 for this limit. And remember, x is going to be some number, so it's going to be this times 1, which is just x minus 3. All right, so the limit as n approaches infinity of all this is absolute value of x minus 3. And we know that this converges when this is less than 1. Now, the ratio test said that when absolute value of x minus a needs to be less than r in order to converge. Well, that means that your radius of convergence then is 1. So the radius of convergence is 1, and we also know that the center of convergence is 3. All right, let's do another one here. Determine the radius of convergence for this series. So we're going to have the limit as n approaches infinity, absolute value n plus 1 times x raised to the n plus 1. And notice that there's no a value on this. It's just x. It's not x minus 2 or x plus 5 or anything. And so that means this is centered at 0. All right, so we have over 4 raised to the n plus 1. times the reciprocal, so 4 to the n over n x to the n. Again, we can reduce some things here. All right, so x to the n plus 1 over x to the n, that will reduce to just x. 4 to the n over 4 to the n plus 1 will be a 4 in your denominator. And then we have times n plus 1 left over n. Now, the limit as n approaches infinity of this is 1. So therefore, the limit of this whole thing is 1 times x minus 4, which is just absolute value of x minus 4. In order for this to converge, this will have to be less than 1, which means the absolute value of x is going to be less than 4, because we can multiply this 4 over to the other side. Now that tells us that the center of our convergence is going to be 0, because it's x minus a, x minus 0, and this is our r value. So the radius of convergence is 4, and the center is 0. So again, what that tells us is that from negative 4 to 4, because our center is at 0 and the radius is 4, from negative 4 to 4, this series is going to converge. Now, we do not know yet what happens at negative 4 or what happens at positive 4. It might converge, it might diverge at this particular number, but everything in between, it has to converge. And we will look at some other tests and get some other tests under our belt, and then look at what happens at these particular values. We always have to look at the endpoints to determine what happens, or what the interval of convergence is. We can't just say negative 4 to 4, because we might have parentheses or we might have brackets. It depends on whether it converges or diverges at this particular number. And again, we will do that a little bit later. All right, so let's take a look at this particular problem, which says use the ratio test to determine whether the series converges, diverges, or is inconclusive. All right, so we are going to write this as a series first using sigma notation, from as n is equal to 0 going to infinity. Actually, let me change this from 0 to 1 in this particular case, of 2 to the n in your denominator, and you're going to have n squared in your numerator. And so this series, we can generate this series from this notation right here. All right, so what we want to do is perform the ratio test using this. So you're going to have limit as n approaches infinity, absolute value n plus 1 squared over 2 raised to the n plus 1 times the reciprocal. And then we want to reduce this a little bit. 2 to the n over 2 to the n plus 1 gives us a 2 in the denominator. All right, then we have n plus 1 squared over n squared. And the limit as n approaches this, well, the first term in this would be n squared over n squared, so limit as n approaches infinity will be 1, times a half is going to give us a half. All right, so since that is less than 1, that means that this series converges. Does not mean it converges to a half, it just means that the series will converge to some particular value that we do not know at this time. All right, and the last example here, we have limit as n approaches infinity, n plus 1 factorial, and then this will be 2n plus 2 factorial multiplied by the reciprocal, and then we can reduce this a little bit. N plus 1 factorial over n factorial will reduce to n plus 1, and 2n factorial over 2n plus 2 will reduce to 2n plus 2 times 2n plus 1. Because after that, you're going to have 2n factorial, which is what cancels with the 2n factorial. Now, if you think about this in terms of, once again, spit in the ocean, leading term in your denominator will be 4n squared plus 6n plus 2. And the limit as n approaches infinity is going to be n over 4n squared, which reduces to 1 over 4n. And as n approaches infinity, this is going to go to 0, which is less than 1. Therefore, this will converge.